Okay, good morning, everyone. Hope you are able to hear me and see the slide.
Yes, sir.
Okay, so happy Shankranti to all of you. So this will be our last class, and we have been discussing about the conformation of cyclics. So we'll mostly confine ourselves to 6-membered ring. And I told you in the last class that you practice little bit how to draw. You cannot be a very great painter, but while writing the 6-membered ring in the chair form, it should really look like a chair form. And little practice will make you an expert in how to write the chair form. So basically, I said like you draw a line as shown here. So about 40° or something like that with the horizontal line. Draw another line of the same length below it like this, and then try to attach like the two ends. So you go like this and this and this and this. So this kind of like a cyclohexane ring, and then you put the axial bond like here as shown. Equatorial will go, and little practice will make you an expert. And equatorial, this is also equatorial, this is axial, this is equatorial like this, and this is also axial. And so conformation for these compounds we have seen previously, unsubstituted one. And if you have a substituent, it tries to occupy an equatorial position. We have said that it is more stable, because in axial position you have something called 1,3 diaxial interaction, 1,3 diaxial interaction. And for a methyl group that destabilizes the system by about 0.9. So you have two of them, so you like a 1.8 kilocal per mole. So it tries to occupy the equatorial position. This also reflects in various other properties of the molecule. For example, one example I have shown here, mostly through static effect, that equatorial one undergoes acylation. If you have to make O acetate, suppose you have to make O COCH3, so this reaction goes faster with equatorial substrate than the axial one. And if you have 1,2 disubstituted compound, and if it is a trans isomer, then you get diequatorial the more stable than the diaxial, because as I said, like a 1-methyl gives rise to two 1,3 diaxial interactions. And so two of them, which is like a amounts to 1.8 kilocal per mole, two of them will give rise to like a 3.6 kilocal per mole. So this will be like a destabilized by 3.6, and this one has one butane Gauss interaction, as I have shown earlier in case of butane, and which is like an angle 60 degrees. So this is like a 0.9 kilocal per mole. So it occupies diequatorial position. And if you have a cis isomer, then like you can they're identical, both of them. So both of them has one axial bond, and so it gives rise to 1.8 kilocalorie per mole interaction, and also 0.9 kilocal per mole Gauss interaction. So from here we went to how to draw the structure. For example, this one is if I write in the planar form, this is 1,2 trans dimethyl substrate, which I said like will be diequatorial, will be preferable. And you draw the chair form as shown here. And if you have to draw the Newman projection, it will look like this. And this is the red color bond. So this, if you look from this side, then you can see the hydrogen is up, methyl is, so this is the carbon here. And you can see that hydrogen is up, methyl is equatorial. The second methyl which is behind is also equatorial, and so this is like a one Gauss interaction. So all these interactions, Gauss interaction or diaxial interaction, also you can see very clearly from the Newman projection. And we then took some example of dimethyl 1,3 dimethyl in case of cis. you can only have this one, which is diequatorial. And in case of 1,3 trans, you can have one methyl axial and then one methyl equatorial. And so this methyl axial will have a 1,3 diaxial interaction. So it is not 1,3 cis is stable than the 1,3 trans. And same logic you can extend to 1,4 trans, which is more stable than 1,4 cis, because the 1,4 trans will remain in the diequatorial form as shown here. So that is more stable than 1,4 cis, which is which is having one methyl in the axial position. So gives rise to 1,3 diaxial interactions. And you keep in mind that by flipping a ring, we don't change the stereochemistry of the substituents. For example, here you have S. Even if you flip the ring, so this axial X becomes equatorial methyl. So this is still S stereochemistry. And similarly, the other methyl, which was like a R stereochemistry, from axial it has gone to equatorial, it is still having the R stereochemistry. We also explained, why cis-1,2 dimethyl cyclohexane, does not show any optical activity. So sometimes we call it meso, but meso is something like if you draw a line across this, and then you can say that one half is the mirror image of the other half. But it is not so, because from the planar form, when you transform it into the chair form, actual like a conformation in which the cyclohexane exists, you can see that you cannot draw that line plane of symmetry to this molecule. But still it does not show optical activity, because I said, like, if you flip the ring by like this one is becoming down, and then this axial methyl becomes a equatorial, and this one here which was like S, this has become axial. And now I have rotated a little bit, just for a better visualization. So I have rotated by 120-degree clockwise fashion by that red color axis that you can see going through the middle of the cyclohexane ring. So I have rotated by approximately 120-degree clockwise fashion. So then this one is basically identical with this rot on the top. And if you put a plane, you can see that these two substrates are mirror images. So that means by simple, like a flipping of the ring, you are getting its mirror image at room temperature or slightly higher temperature. So you will see only the this gets compensated, like a rotation by one enantiomer gets compensated completely by the other one. So you don't see any specific rotation. At a low temperature, you may be able to see some specific rotation if it is a chiral molecule. Now from here we also explained how some other physical properties of these molecules change. For example, if you have an equatorial bromine, an axial bromine, in case of equatorial bromine, the hydrogen is axial, and so it gets little shielded by the hydrogen in the 3 position, so 1,3 diaxial interaction. So it is slightly upfield. It chemical sheet values is more towards on the right hand side, whereas if it is equatorial, it is like a 3.3, and so actually people are able to see 3.2. So at low temperature, possibly you can see both the isomers, 2 peaks, but at room temperature you see an average 3.2. So from there they can calculate what is the percentage of molecule that remains in the cis form, equatorial form with the bromine, and what percentage of the molecule remain in the axial form. So it's like a 83% or 84% remain, which bromine occupies the equatorial position. So by doing this kind of experiment, NMR and all, you should be able to see what like a conformation this cyclohexane ring is taken, and what is the orientation of the substituent. I also gave an example where you have, like a 4 tertiary butyl cyclohexanone. When I try to reduce it with borohydride, so there are 2 possibilities. Hydrate can come from the equatorial side, or it can attack on the axial side. So this gives rise to axial OH, and this gives rise to equatorial OH. And you can also find out from kind of and other experiment that is a ratio of these two. And so attack from the hydride can have some static hindrance with the other hydrogen that is present here. So that is why sometimes a very crowded like a borohydride reagents as you have here that will give like a more of the equatorial attack, and so they cannot approach from the top side, and so it gives more of this axial OH, and hydride is coming from the equatorial position. So all these things are because of the like a conformation which plays very important role in the reactivity and like substituent orientation in these molecules. I have asked you to look into the structures of these, cis-decalin and trans-decalin, and cis energetically higher than the trans-decalin. And in these cases also, you should be able to draw very clearly the Newman projection. So suppose you take this bond, in case of trans-decalin, this bond and this bond. So if you look across, from the front side into this molecule, so you can draw this kind of Newman projection, and then you can see that front side it goes like this, and again like it goes and like this. So both the CH2s are above here, and back side you have below, and this one is below, and then you can draw this ring. So not very difficult. With little practice you should be able to draw this structure nicely, and this one, and of course one more here. And so these are hydrogens. So I have when there is no substituent, these are hydrogen, and if you have substituent, you can put the substituent as you have them, and this is the hydrogen. In case of cis-decalin, so you draw the first ring, so you draw like this, and then you can draw something like this, and another one will be like a bottom here, so you can draw like this. So something like this, or you can see that this is the two hydrogen. One hydrogen will be here. I think I've drawn it wrong, or this one is hydrogen. So this is the cis hydrogen. Whereas in this case, you can see the ring junction, the two hydrogen, one hydrogen here, one hydrogen here is trans. One hydrogen going up, one hydrogen coming down. Here in this case, the ring junction has a two hydrogen, which is like a 60 degree. And this is how you draw these structures. So this is the cis-decalin. So I'll show in the next slide. So this is the trans-decalin, and this is the cis-decalin. So in case of cis-decalin, you what they say, like a cis-decalin had 3 extra butane-Gauche interactions than in trans-decalin. So the cis-decalin can go from one chair to the other, but in trans-decalin you cannot flip the ring. It is very stable system. And in case of cis-decalin, some of these 3 Gauche interactions are shown here. So you can see that if you see across A and B rings are there, this bond particular. Then this substituent here coming down up to 5, and this substituent from this center to substituent 8. So 5, 8 has a Gauche interaction. And same thing, 5 will have it with a 10 also. So if you are considering this bond here in the middle, so then this 5 has Gauche interaction with this 10 carbon. And similarly, 3 can have with a 10. This 3 here can have with a 10. So these are, they're saying, like a 3 Gauche interactions, which are not there in case of trans-decalin. And of course, if it flips also to the other chair form, then you can find out the corresponding 3 extra Gauche interactions in case of cis-decalin. And that's why it is less stable than the transdecalin. And as I said, like it can go from one chair to other, and energy barrier they've calculated at 12.6 kilocal per mole. Now, one of the most important thing for 6-membered ring is like our examples are the hexoses or pentose sugars in the pyranose form. So like when we write a glucose, glucose can be written, what you have learned so far, writing like this, hydroxyl groups and so on. This is a CHO, this is CH2OH, and different hydroxyl depending on what kind of sugar you have, and like this. And then like when you come to the higher class, like intermediate stage, then you learn how to draw the sugar structure and different ways. So I draw a structure of a glucopyranoside like this. It's a planar form. So it is called alpha D glucopyranoside. D because we have learned earlier that it is a D configuration. So that is why D glucopyranoside. Alpha is because of this anomeric position. If hydroxyl is down, then we call it alpha. If this hydroxyl was like this, up, then we call it beta isomer. So this structure I have drawn is alpha D glucopyranoside. Pyranoside is pyranose form of the ring. If it was in the 6-membered ring, glucose can also be drawn in the 5-membered ring, and then like this will be OH and OH and hydroxyl groups here, and then this is OH. So this is a furanose form. Furanose form, and this is the pyranose form. Pyranose form gives rise to 6-membered ring. Now I have drawn this structure in the chair form. On the right hand side, you can see I have drawn in the chair form, and you can see that all the hydroxyls substituents on these are occupying equatorial position except the anomeric position. Anomeric position, as I said, like this is alpha. In case of beta, OH will be this side. So that's the difference. But normally, at room temperature, if OH is not protected, it can go back and forth. You can get a mixture of these two compounds depending on the solvent and temperature and so on. And other substituents like OH here in the 2 position, 3 position, 4 position, and in the 5 position substituent CH2OH, they all occupy the equatorial position. So you should be able to draw this structure, and don't draw, transform this one into this chair form, because you can say that, okay, this I can draw in the different chair form by flipping this ring. But you can see that by flipping this ring, you don't change the chirality, but you change the orientation of the hydroxyl. So all the substituents have become now axial, so which is not energetically feasible, favorable. So you draw this. Don't draw this chair form, but you draw this chair form. And of course, they have some names, but I will not go into all those details. But it will be obvious to you that it is more stable, and this is the chair form that glue in. Sometime in the books you can also see it is written like this. So this is also another way of drawing 6-membered ring in the it's not exactly in the chair form, but it gives a 3-dimensional picture of. I said earlier that if you have a 5 pentose sugar like carbon, so you can have also a 6-membered ring if it remains in the pyranose form. You are taking, the substituents occupy this kind of position. For example, like this hydroxyl here in glucose, this hydroxyl, I'm circling here. So this is down, and if you have a mannose, so mannose is basically a diastereomer of glucose, then this hydroxyl will be up. So this will be up. Similarly, if you go to galactose, galactose has particular hydroxyl like this one up here, and so it depends on what sugar we have. You can draw the structure very easily. And of course, that so much I wanted to tell you about the 6 and 5-member ring. It is little bit more complicated, but it is for your information. We will not go more in details. And see, if it is completely planar form 5-member ring, so there are lots of eclipsing strain in the planar forms, and so there is although there is no angle strain, but you can see that any of these bond that you take, it is completely eclipsing all the substituents in both the carbon. So it does not remain in the planar form. So it tries to reduce the strain from the eclipse form by going into some envelope. Envelope is very easy to visualize that 4 of them are in the plane. These 4 are in the same plane, and one of the substituent is coming up. And then it can further reduce the strain by going to the twist form. You can play around, and then you can see that this portion is coming towards you, and then one bond goes up and then comes down and goes like this. And this is how like a conformation of the 5-member ring takes place. And you can see the like there is a half chair form, and that is the most stable, and there is one envelope form, and of course the most unstable one will be the planar form. And it can go from one to the other, and this is very important for understanding the structures of DNA and RNA and so on. So this particular case here is sometimes we call C3 prime exo, and C3 is like this carbon. So if you take what do you call furanose form of the DNA or RNA, so we call this position as 1, 2, and 3. So if it is down here, so then we call it C3 prime exo, and then if it is up, it is called C3 prime endo. And sometimes it is called S type, conformation. It's like S more. I try to remember as a south. And in a map, you see that top part is the north and bottom part is the south. And if it is a endo, it is sometimes called N type. And so, I mean, if you go to DNA or RNA, so the puckering of the ribose ring plays important role in the overall 3D structure of nucleic acid. And like a RNA is predominantly C3 prime endo. So that means like you have particularly this conformation in case of RNA. So you can see there is an oxygen here. This is the base. The nucleobase is attached. Then 2' position, and you call it 3' position. So 3' endo is like a conformation. And it is C2' endo. Sometimes it is called B conformation. And like as I said, RNA C3' endo. DNA may adjust and is able to take both the conformation. So this much is like sufficient for you to know the conformation that 5-member ring, different conformation they can take. And from there you can go to maybe cyclobutane. Cyclobutane even more difficult because you can see this completely eclipsed, and this bond angle of course is 90 degree, and this is like a planar form. So this planar form is the most unstable one, and then you can go to little puckered form, and the puckered form will be like a more stable. And this way it tries to reduce the strain angle. And if you can see in the puckered form, this inside angle is less, but at least they are getting out of the what do you call the eclipse form. And some of the bond angles in the puckered form are given here. So inside, as I said, like you have you cannot control. So these are around 90 degree. But this one is like a 110 and then 107 degree and so on. So this is the conformation of cyclobutane, and those who are interested, you can read conformation of cyclopropane ring. Cyclopropane also is a known substrate, and it is a more strained system, and under very mild condition one can open activate the cyclopropane ring. And okay, I think I'll stop here today. So in this course, what I have tried to do is give you some flavor of everything that you need to know about stereochemistry and conformation. So we started by learning about the elements of symmetry, that how do you say that if a molecule is chiral or not, and what kind of symmetry elements are present in a molecule. And we have also given some assignments in which you might have seen, you have to visualize, what kind of elements of symmetry are present in those molecules, whether those molecules are chiral or not. Once you know these molecules are chiral, then we learn how to assign the configuration, RS configuration into those substrates. Earlier they were using D and L kind of configuration, but nowadays we mostly use R and S. So we learned the priority, how to prioritize the substituents, Kahn, Ingold, and Prelog formulas, and from there rules, and from those rules you learn how to define. So once we learned how to define, and then we learned a little bit of the physical properties. One of the most important physical property of chiral molecule is optical rotation. So we learned, like if it is a meso compound, or if it is a racemic mixture, or if they don't have any, chiral center, they will show optical rotation 0. But chiral molecules show, some optical rotation, and you can calculate the specific rotation by dividing the actually found rotation with the concentration and the length of the cell and so on. Some formula is there. From there you can find out again like an enantiomeric excess. Suppose you have 80% of R isomer and 20% of S, enantiomeric excess will be like a 60%. So these are the things we have learned. And then once you have a mixture, like a racemic mixture, for example, we learned a little bit about how to separate them, how to do like a resolution. If it is amine or it is acid, you can make the salt with the corresponding acid, chiral acid, which are commercially available, should not be very expensive. And from there you can go to if it is an acid, you can use a chiral amine, and once you make the salt, it will precipitate out if you are lucky, and then collect those salt, and then you can remove one of the components by doing the acid base workup and get the chiral molecule. We also learned how you can separate isomers, stereocenter, by making a covalent bond. So with a chiral molecule, I gave an example of phenylalanine. Phenylalanine is something which you get from phenylalanine by reducing the acid, and then it can be used to, for example, if you have an acid, you can make an amide bond, and then it becomes a diastereomer. So because the phenylalanine is like a chiral we have used, and you had R and S mixture of the acid, and so you separated after making the covalent bond, you separate those isomers chromatographically. Once you separate, take the pure diastereomer, and then you can do the hydrolysis of the amide bond. It could be an ester also. Suppose you use a chiral alcohol like a menthol or any other chiral alcohol, if it is commercially available. If you are lucky, you make a covalent bond, and they should be separating, in the TLC. Chromatographically, they should have a different polarity so that you can easily, separate the two diastereomers. And after doing those, then you can, cleave the ester bond by treatment with the base. So we have also given example of the Mosher ester and so on. Once we know how to separate them, then we try to learn some stereo selective reaction and stereo specific reactions. Specific reactions are those where the mechanism of the reactions are such that you get only one isomer, like SN2 kind of displacement of a chiral center. So you get the opposite stereochemistry when you do SN2 type of reaction. And also we have learned, like a bromination, for example, of a double bond. It gives rise to dibromide, and then like a mechanism also that you get a bromonium species and the other bromine comes from the other side. So you get an anti, addition into your addition of the osmium tetroxide or potassium permanganate. So you get a diol, 1,2 diol from an olefin. And we also, I think, given an example how to get a 1,2 trans diol from the corresponding epoxide. So you can make an epoxide and then it opens up to get a like a acid catalyzed opening. Suppose like epoxide can treat with H plus, and then a nucleophile will attack the epoxide and give a 1,2 trans product. And so this also certain mechanism of the reaction such that you will get only those kind of product. We also saw shown examples of like a hydrogenation. Catalytic hydrogenation gives a syn addition of the hydrogen, and yeah, that's about all. And then we went to stereoselective reaction. One example could be diastereoselective or enantioselective. One example, very famous one, we talked about the Sharpless epoxidation of allylic alcohol. So you need an hydroxyl group there for the mechanism of the reaction, and I have shown you how you have to draw the allylic alcohol vertically, the double bond, and then CH2OH coming down and towards the right hand side, and then you can predict which epoxide you will get depending on which diethyl tartrate you are using. If it is a natural tartrate, it comes from the bottom side. If it is a unnatural tartrate, it comes from the top side. And application of one of those good application for this was like if you have a chiral center next to the hydroxyl, then you can do like a what is known as kinetic dissolution. So one of the isomers only undergo epoxidation. The other isomer does not undergo epoxidation because of the static hindrance. So you get a pure allylic alcohol, enantiomerically pure, and enantiomerically pure epoxy alcohol. And yeah, from there we think also learned little bit about getting more of the chiral center through aldol reaction. So you make an enolate. I showed how the stereochemistry of the like a final product depends. Relative stereochemistry depends on what kind of enolate you get, whether it's a Z enolate or it is a E enolate. So there are reagents which gives you selectively the cis enolate, Z enolate, and there are reagents which gives you selectively E enolate. And in case of Z enolate, you get the syn product, and in case of E enolate, you get the trans product. And some examples I showed where like if you have a chiral auxiliary attached to those enolate, then you can have the reaction taking place only from one side of the enolate, because the other side gets blocked by the bulky substituents that is present in the chiral auxiliary. And so after doing this reaction, you do remove the chiral auxiliary. One of the examples I showed like a lithium perhydroxide, and with that substrate you get an acid. You remove the chiral auxiliary. There are other reagents like lithium aluminum hydride or diol which can give you the alcohol. And then like this also can be used for alkylation. Suppose you have enolate, you can do CC bond formation by using a halide, simple allyl bromide, or crotyl bromide, or simple methyl iodide, or anything, any substituent. You can alkylate the position. One example I showed where Diels-Alder reaction also takes place very selectively. And then we started learning a little bit about conformation. We talked about ethane. Then we talked about, I think, butane, and how the two methyls will try to be against each other. But it depends on kind of substituents. I have shown like if you have a hydroxyl like a 1,2 diol, then those two hydroxyl would try to be in the 60-degree gauche form, because it can have intramolecular hydrogen bond in that form. So the cis one gets, gauche one gets more stabilized. So as compared to the anti-orientation of the 2-hydroxyl. And then like we talked about some of the cyclic molecules like cyclohexane, and how substitute cyclohexane, like what orientation they take, equatorial position, as compared to the axial one. So axial one has 1,3 diaxial interaction. So keeping this mind, 1,3 diaxial interaction, each one methyl groups, only methyl you can remember 0.9 kilocal per mole. So if you have 2 1,3 diaxial interaction, it gives rise to 1.8, destabilizes by 1.8 kilocalorie per mole. One intramolecular hydrogen bond stabilizes system by 5 kilocalorie per mole. One butane Gauss interaction also like a 0.9 kilocal per mole. So these are the numbers which are not very difficult to remember. Few numbers you can remember to explain, some of those products. And like I have shown you how to draw the chair conformation, and especially with terms of glucose and any hexose sugar, and you should be able to draw 6-membered ring and put the substituents at as they are present in the particular sugar. So this is about all, and so in between, of course, we have talked about, I think, pro R, pro S kind of nomenclature. Then we have prochirals, carbonyl group also, psi or reface. We have learned about helicene, conformation, how to define, left-handed helix or right-handed helix, like a, and give them in the nomenclature like a R and S configuration. So most of the things I tried to cover, and it's only like a 10-12 lectures. It is not more, and I also don't want to burden you with too many things to teach in this course. But those who are interested, and especially those who come in chemistry, they will have more opportunity to learn. Those who go to biology, they will also remember, like a conformation of protein, amino acids and protein, and this particular, like a conformation of the sugar packaging in DNA, RNA. They play a very important role. So, so I wish you all the best, and you have, like many of these things I did not learn during my, undergraduate courses. Although I studied, some of the best schools, which departments in the country, but nobody taught us. In many of these things, even after my MSc, these things were not taught. And so I learned it on my own, and I thought now you people are intelligent, so it is an opportunity for you to learn, at least get to know some of the basics of many of those things. You learn, as I said, like a more as you do more courses in future. And I hope many of you would take chemistry as the major. Chemistry is a good subject, and you, even if you go to biology and many other areas, possibly if you are strong in chemistry, you will do possibly, in my opinion, you will do better. And you have a quiz tomorrow at 8:30 during the tutorial class. So 10 minutes before or 15 minutes, I'll upload the quiz question and complete that. That is the last quiz. And then next week, I think 20th, you have the exam from the UG office. You must have received the schedule from 2 to 4. So join there for the 2-hour final exam. And as I said, wish you all the best. And if you have any doubt, any question, you can ask me now, or you can email to your teaching assistants and get clarified by them. Okay.
Hello, sir.
Yeah, somebody has some question.
Yes, sir. Can you hear me?
Yes, Ravan. Yeah. Yeah.
No, sir. I'm Anubhav. I wanted to ask, what is the syllabus for tomorrow's quiz?
Your voice is breaking. I don't know whether my internet problem or something, or you can
So,
type your
what
question
is
also.
the syllabus for tomorrow's quiz?
Maybe like up to here, or whatever I have been taught. So it will be a mini final exam. It will be one way. It will be good for you. So you can read as much as you can. So it will give you an idea what you expect in the final exam. So not very difficult, as you have seen. Even assignments you have done all this. So it should not be very difficult ones.
And sir, one thing I wanted to clarify: the final exam, is it open book
But
or closed book?
yeah, you can take your class notes. Whatever I have. posted that those are available to you. 2 class notes are there, files, so you can look from there. But you don't. I expect you to maintain what do you call honesty and all while writing, because there's no way that we can invigilate. So you do not discuss with others, but you can consult your like notes that I have already sent to you, that you can check, no problem.
And sir, can you discuss once more the iodolactonization reaction, the stereochemistry? Actually, I had missed the
Which
class,
one?
and in the slide, not a lot is written. Iodolactonization.
I'm not able to hear you properly. I don't know. Can you write it down, like in the chat box so I can see? If somebody, you can write, I will look into it. And Anubhav, if you have a question.
He's saying iodolactonization.
Iodolactonization. Okay. So you have seen one example I gave, in one of the slides earlier, how iodolactonization. So you form an iodonium 3-member ring with the double bond, and the carboxyl group comes and attacks, from the opposite side of the iodonium, and that's all. And of course, if you have two possibilities, suppose you are getting a 5-membered ring and 4-membered ring. So you know that 5-membered is more stable than 4-membered. So you write the structure of the 5-membered ring, not the 4-membered one. And the iodine will be like onto the next carbon. Nothing more than that you need to know. So basically onto the double bond you put an iodinium like a dotted line at the bottom, and or at the top, depends on which side is less crowded. And then like a carboxylic group COOH, oxygen will come and attack the nucleophilic attack onto that carbon, one of the carbons. And the other carbon will then the iodine will go to the other carbon. Okay.
Sir, while forming the ring, how can we decide from which side, as in which substituent plays a role in deciding from which side the iodine ring forms?
Maybe some substituents will be there, and I have shown earlier, like a basically, like in a allylic 1,3 allylic strain. So double bond and like a hydrogen will try to be on the like a planar form, and the substituent 1-methyl or something is there. It will go up or it will come down depending on the stereochemistry. And so if methyl is tell me.
If the substituent is not at the alpha position to the double bond, if it is at the beta position to the double bond, then what will happen? Will it affect the stereochemical outcome?
I mean, yeah, I mean, of course, it depends on, like a iodinium is formed, and then you can get two products. It is not, that you'll get possibly only one product, and you can get two products, but the actual final product which you get will have opposite side attack onto that, like a iodinium coming from the opposite side of the alpha substituent or beta substituent.
Okay, sir. Thank you.
So, sir, for the beta substituted compound, it'll be like there's a possibility of two products, right? And I mean, how will you decide which one is the major one and which is not?
Which one in case of the same iodolactonization?
Yeah, like you said, the beta substituted one, right? In that there'll be one major and one minor.
Yeah, sometimes it is. Yeah, sometimes also product. What do you call? Stability also decides, what product you will get. There's a kinetic. I will not go into the details. Thermodynamic control and kinetic control. Sometimes the product. If you draw the energy diagram, you will see that one product is more stable than the other product, and then there is a way that you can get more thermodynamically controlled product than the other one. So like as a thumb rule, you can always say that the product that you get, major one, should have less crowding than crowded steric hindrance than the other product. Yeah, so that should clear a little bit, like a final product. If there are two possibilities, even if it is a beta position, the final product that you get, if one of them is energetically more stable, then that is more likely to get formed in more quantities. So that's the thumb rule, I can say.
Okay, thank you.
Okay, yeah.
Sir, in slide
Yeah.
44, there is a table for
Let me
1,3 diaxial.
I don't remember those things, but as I said, like if you go from methyl to tertiary butyl, it is more interaction steric. Electronic is also there, some substituent. But I just, I just copied from somewhere. I got that table. Only you try to remember for the methyl. We will not ask anything. Yeah.
Like bromine has lesser energy compared to methyl. So does that mean that bromine is preferred in axial compared to methyl?
Yes. So
Like
if you
in that
see that.
table, bromine had lesser energy than methyl.
So that
So,
means, like what happens is like a carbon is smaller than bromine. Okay.
yeah.
A carbon atom is smaller than bromine, but when I talk of methyl, there are hydrogens are there. So 3 hydrogens when you put together, I don't know exactly what will be the dimension of a methyl group, but I assume that it will be bigger than bromine. No?
So there'll be more steric hindrance because of methyl.
More steric hindrance as a whole. Yeah. So that's why in case of bromine, although bromine, iodine, these are of course much bigger than carbon, but once you add two hydrogens and a whole thing from one hydrogen to other end, like if you draw a circle kind of thing, so they may look bigger than bromine. Then I guess that possibly the reason why methyl shows more interaction, 1,3 diaxial interaction than bromine. Yeah, sometime you may have this like a you have to decide whether bromine will occupy an equatorial position or compared if one carbon is having methyl and bromine, which one will occupy equatorial more favorably. And so you can say that okay, methyl should occupy the equatorial position and bromine should be axial because it gives less 1,3 diaxial interaction. Hmm?
Yes.
Yeah. Anybody else?
Yes, sir. Sir, in today's
Yeah, Anubhav, I think I might have answered your question. You have written there in the chat box, but already I have said, basically at the end, the product that you get should be sterically less crowded and more stable than the other one. Hey, anybody else has any question?
Yes, sir. Sir, coming to today's lecture, sir, you showed that ring flipping can happen at room temperature, right? So how exactly does this flipping occur? I didn't quite understand.
Ignis, suppose 1,2-dimethyl cyclohexane. So if sometime you see two different like a conformation at low temperature. If I do the experiment NMR, then I should be able to see two different conformation. But when I raise the temperature, interconversion, because when you have seen like a energy diagram, cyclohexane going from one chair to other, so it has to pass through some of the energy barriers. And those energies are available if you do at like a 27, 28 degree, 30 degree, 40 degree room temperature. So those interconversions are very rapid. So you see an average picture. Huh? But so if you chemical shift, suppose I wrote like a bromine. If you have equatorial and axial bromine, then like a hydrogen attached to that one is having 3.3 something is like a 2.7 in the pure form. Suppose I could do an experiment and minus 20 degree temperature, and then I get both the isomers and I can see the NMR peak. But when you do room temperature, they convert interconvert so quickly, so you see an average picture, just like rotation also. So why you see, zero rotation in a racemic form, because both plus and minus are, rotating the light. But statistically, if you see so many molecules are there in the system, that, if you have 50-50, then it gets completely, like a balanced each other. So you see an average picture when you do at room temperature. I have given another example of methyl. Suppose you have a methyl, it is coupling with an alpha hydrogen next position. So the dihedral angles are not same. So some hydrogen with the next hydrogen is having 60-degree angle, one hydrogen having 180-degree angle. But what you see in the NMR, I see only like an average coupling constant. So this rotation or interconversion is possible at room temperature, but at lower temperature you can have different conformation. I mean both the systems can exist. Yeah, is it okay?
Yes, that's okay. But sir, coming to the NMR thing you were mentioning, say like I
Yeah.
have like 100 atoms, and then like half of them are in one conformation and half of them in the other conformation. Now say for one conformation we'll get some particular delta value, and for some other for the other one we'll get some different delta value. So because there are like half and half, so since we get two peaks for both the delta values, but in the slide you mentioned that there'll be an average delta value. I was thinking there'll be two different peaks, right? Why will we get average?
Let me see if I can bring back that slide. Suppose this example, yeah? Is that one?
Yes, example is.
Can you see?
Yes, sir.
Yeah. So you can see that if I had only this particular hydrogen, then this hydrogen is appearing at 2.7. And if I had only pure this one, then this is having 3.3. And this possible if I do that, like at low temperature, and then possibly I can freeze it in particular most stable one, and then it does not interconvert to the other one. And at some temperature, maybe I'll see 1:1 of these two, and then you can see these two peaks. So one will be here, 2.7, and another will come here, say 3.3. But at room temperature, slowly what happens, like we do variable temperature study. So we do -10, -20, -3. So these two slowly you can see, like it's coming between 1, that is 3.2. So they will change, and then interconversion is so quick that, like you see an average value.
Oh, okay. That makes sense. So thank you so
Yeah.
much, sir.
Yeah, sure. Okay. If there is no other question, then I will log off now. And I wish all the best. Rashi, you have a question? No? Your hand is still raised?
Sorry, sir. I forgot to lower it.
No problem. Fine. All the best to you. Okay. Tomorrow, don't forget the quiz at around 8:30. All right.
Thank you, sir.